Hi there, today we'll look at self-training with noisy student improves ImageNet classification by Qizhi Xie, Mintan Luong, Eduard Hovey, and Kwok Vi Le. So this paper takes an ImageNet classifier that's been trained on the ImageNet dataset and uses that classifier as a teacher model to label a whole bunch of unlabeled images. And then it trains a student model that is larger than the original teacher model on those teacher-labeled images. And that turns out to improve the classification on the ImageNet validation set. Now, that there is a couple of things that make this all work. And today we're going to explore how this paper does it and what they say is important. If you enjoy content like this, as always, don't hesitate to share it out or tell your friends about it. And if you're not subscribed yet, then do so. I would appreciate that, and you'll get more content. So win-win. So this paper is about semi-supervised learning in effect. So it's at the intersection, actually, of semi-supervised learning, knowledge distillation, and transfer learning. So what do we mean by semi-supervised learning? Usually in supervised learning, you'll have some sort of data set, and the data set will contain, let's say it's an ImageNet, it's image data set. So the data set will contain images. This is an image with like some sort of cat on it, and it will contain the labels according to that, so cat. Now, in semi-supervised learning, you assume that, so this is supervised learning. In semi-supervised learning, you assume that only part of your data set has the labels. So, like, only this part down here has the labels, and the upper part does not have the labels. So that's semi-supervised learning. It's often the case when it's very expensive to get labels, so you can only get labels for a couple of images in your dataset. But very often in semi-supervised learning, you still assume it's the same data set. There is a slightly different setup here that's called transfer learning. So in transfer learning, what you'll have is you'll have your data set that has the labels, but it's very small. So you'll notice I've drawn it smaller. That means you have very little. That is also the case when it's very expensive to get labels, but also it's expensive to get the data itself. This is often the case, let's say, in medical data, where not only is it expensive to get labels for like a CT scan, it's actually expensive to get the CT scan. So what the goal in transfer learning is to say, well, I do have only this small data set, but I do have this giant other data set over here. Now, can't I, it's not the same. Maybe they're not CT, so these are CT scans. Maybe these are X-rays, right? They're fairly similar technology. If you slice the CT, it'll give you sort of an X-ray. Can't I, train my model, pre-train my model on X-ray data, and then fine-tune it on the CT data? So that's called transfer learning usually. Now, this can be done with or without labels. So it can be that for the X-ray dataset, you do have the labels or you don't have the labels. There are techniques for all of those. Now, what we're going to look at today is kind of this situation right here. It's the transfer learning situation where you do not have the labels for this X-ray dataset. But other than in this X-ray example, what we're going to look at is the small dataset is going to be our ImageNet database. So our original picture with label database. So you'll see immediately the difference here is that in the transfer learning setting, we usually assume that the dataset we want to train on is fairly small. Here, ImageNet is already sizable. But what we have is we have a much larger database of unlabeled images that we can just get from the internet. So we can scrape the internet for any kind of pictures, and that will be our unlabeled data set. Now what we'll try to do is somehow incorporate this unlabeled data set here into the training process to get better on the ImageNet data set. Okay, so this is the problem statement is you have the ImageNet dataset and you have a second much larger dataset of unlabeled images, and you somehow want to make use of them. So I hope you see how this is sort of connected to the others. It's essentially sort of a transfer semi-supervised learning setting, but with the exception that usually in transfer learning you assume that the labeled dataset is like super small, which is not the case here. And that's going to result in us being able to apply a different technique. So this different technique is called the noisy student. Now, usually what you might do in a transfer learning setting is you might want to start with that big data set, right? Because that's the data set that's sizable enough to allow you to train a really big model on it. And then you fine tune and you sort of hope that the information transfers over. Here, on the other hand, what we want to do is we start with the ImageNet dataset. So first, we train this in a supervised learning fashion into our model. Now, this model is going to be called the teacher model. We know how to do this. We know how to train ImageNet models, right? So we can train this into a teacher model that has reasonable accuracy on the ImageNet dataset. Step 2, we're going to take that big dataset over here and use the teacher model to label the unlabeled images. So for each image coming in here, the teacher, so maybe this is again another cat, the teacher will say, that's a cat. Okay, so that gives you the big data set where now you have images along with labels. Just the labels aren't true labels, they're generated by the teacher. And then in the third step, you train this big data set. You train on this big data set, and that's what you call your student model. And then the student model in this paper will see how can we make it such that the student is then better at the original ImageNet task than the teacher ever was, which seems counterintuitive at first because all of the information that the student is trained from is basically what the teacher already knows, right? All the labels here come from the teacher. Therefore, the student shouldn't be able to outperform the teacher. But in this case, the student will be able to outperform the teacher. And their argument here is that this is mainly due to the fact that you use noise in this training procedure. So when you train the student, what you'll do is you'll use noise. And one of the types of noise is that you severely augment this data right here in order to train the student. Now, we've known for a long time that data augmentation, for example, in the frameworks of self-supervised learning and so on, can have a very large benefit to training. And here, the fact that we incorporate this extra data and we use noise and augmentations on it is going to result in a student that can sort of learn more about the data than the teacher did know. Okay. This is basically it. And as you can see, this is kind of their main final results, where they say on ImageNet, our top 1 accuracy sort of increases right here. And even on these kind of subsets of ImageNet, or these are sort of corrupted sets of ImageNet, they make even more substantial improvements, as you can see here. Now, we'll go into what these corrupted subsets are, but just for now, these here are very difficult variants of ImageNet. They can be severely corrupted or distorted and so on. And you can see that the model improves severely over the previous state of the art, which basically means that this model is more robust. And that's a direct consequence of the noise. Now, one last thing I should say is that the student here is also larger than the teacher. So that's also one thing that makes the student better. So what you will make is the student model is larger than the teacher model, as the architecture. So in combination with the noise right here, in combination, that means the student model is probably able to capture more of the variance of the data. It's larger, it has more parameters, it can learn more about the data. Together with the noise, it can probably be more robust, and that's what makes it generalize better. And we'll also see, as we see here, it's more robust to these transformations, and it's also going to be more robust to adversarial perturbations. So the technique again is illustrated here. As we said, it's pretty simple. First, so step one, train the teacher model with labeled data, as you would. Step two, you infer the pseudo labels on unlabeled data. Step three, you make a student, we'll step three over here. Train an equal or larger student model with combined data and noise injected. So they use the original labeled data here and the pseudo labeled data right here in order to train the student. But still, the student doesn't have more information, more label information than the teacher had. It simply has this teacher labeled unlabeled data also to train on. Now, the crucial part here is, well, first of all, that the student can be larger, and second of all, that there can be noise. And the noise comes in three different forms. So first of all, you use data augmentation, which we've already seen. This is sort of like random cropping or mild rotations, color jitter, whatever. They use a rand augment here, which is a specific technique to apply these augmentations. They use dropout, which is a fairly old technique where you, in the student model that you train, you randomly drop out connections, which makes it more robust and more generalizing. And then you also use stochastic depth. Now, stochastic depth is a technique when you train a model. What you'll do during training, instead of always passing your data forward through the layers like this, you use some sort of a dropout, but with entire layers. So what you'll do is you'll pass your data forward, and then randomly you'll skip a layer and then pass it forward again. Now these might seem weird first because it might seem weird, but if you know that most models, especially computer vision models nowadays, are residual networks, which means that their layers look like, so you have the input, you have some computation, and then you have the output, and then there is already a residual connection that basically adds the original signal together to the result of the computation. So all you do in this stochastic layer dropout, or this stochastic depth right here, is you basically disable this connection right here, and all the signal has to flow through here. If you read the original ResNet paper, they make it pretty clear why the residual connection is a good idea. Basically, they say these computations here, if you have a very deep network, each layer only has to basically do a little bit of computation that can be bypassed fairly efficiently for a lot of data points. So it's not that hurtful to bypass a layer. And in this case, they actually use it to just bypass some of these small computations and inject some more robustness into the student model. So with these three strategies to bring noise into the training process, one is on the data and two is on the student model itself. They train the student model. And then fourth, and this is what we didn't have before, or maybe we put 4 here, make the student a new teacher. So now you can iterate. You can use the student model that you just trained to again label the unlabeled data. And then you can use another student model, again under the influence of noise, to train from that student model, and so on. And you can go on. And they do up to like 3 iterations of this, where they always take the student as the new teacher, and then use a new student model to train from that teacher. And they get better and better as they do this. Of course, there's like a diminishing returns, but it's pretty impressive that this even works, right? The new students, in fact, aren't even larger than the old students. It's just that the students are larger than the original teacher model in most of these cases. So here's the algorithm written down. You'll require labeled images right here and unlabeled images, which are the ones with the tilde. So first, you learn the teacher model, which minimizes the cross entropy on labeled images. This, we already know this, right? This is the label, this is the image according to the label, and you train the teacher model, which is this thing here. And you can see here, noised. So already in the teacher training process, you want to introduce this noise, you want to introduce these data augmentations. These are, as I said, these are standard techniques to make models more robust and therefore more generalizable. Yeah, we know from these self-supervised papers that these augmentations are very powerful, and the way you design them, basically, one of these augmentations is a random crop, which means if you have an image, you randomly crop out like part of that image, and then that's your training sample and not the entire thing. So by doing this, you basically teaching the model to ignore the exact location and scale of things on an image. And you can do this because you as a human know that, I can zoom in, I can zoom out into something, and it won't change what's on the picture. And so you use these augmentations to kind of heuristically tell the model what it should be invariant to. And that is a very powerful technique to regularize, basically to robustify these deep methods. And this is used the same here. So already in the teacher model, we train with this noise. And then step 2, use a normal, i.e. not noise teacher model to generate soft or hard pseudo labels for the clean, i.e. not distorted, unlabeled images. And this is important. They stress this here, that when you label the unlabeled images, you want to use the model that is without the noise, and you do it on the not distorted, unlabeled images. So when you infer the labels, it's very important that you have clean, accurate labels without any sort of noise in them. So label noise is not something that they have found to help in this case. So not label noise on the teacher, that is. So you can see right here on the unlabeled images, we'll use that teacher model without the noise to infer the labels. Now, they say these can be hard labels or soft labels. So what does that mean? If we generate hard pseudo labels, that means that the y here is simply going to be either 0 or 1 or 2 or 3 and so on. So just the index of the class. Whichever class is most likely, that's going to be our label. This is exactly how the supervised data sets come, right? So this is what you'll think first when you see that. However, soft pseudo labels means that the y will be a distribution. So instead of being of class 0, it will be sort of, let's say, 90% of class 0, but also 5% class 1 and 5% class 2. Right. So you'll output the distribution instead of just the label. And they have found that the soft pseudo labels work slightly better than the hard pseudo labels. Okay, thanks. So they use the soft pseudo labels here because they work slightly better, but you can do it with hard or soft labels. The important thing is that you use the teacher to generate as accurate as possible labels for your unlabeled data. Then, third, we've already seen this, learn an equal or larger student model, which minimizes the cross-entropy loss on labeled images and unlabeled images with noise added to the student model. So, as you can see, labeled images and unlabeled images. So we're in this semi-supervised learning setting right now. You take in both together with noise. And noise here is in bold, which means they stress it again. This is important. So you can see that the loss is composed of two different things. These are the true images of your original model. And you use that, and this means you noise the student model, and that noise can be on the data or in the model itself. And here, also the unlabeled images that you have labeled with the teacher, you do the exact same thing. So you train on both of these data sets. And step 4 is, if you want to do iterative training, use the student as a teacher and go back to step 2. Now they have some more tricks when they do this iterative training. They also up the batch size during the iterative training and so on. So they do a lot of things to make the student learn something more, something better than the teacher. And I think the whole paper, it doesn't state it explicitly, but I think the whole paper, everything they do here is to kind of force or allow the student to become better than the teacher by giving more noise, by making the student larger, by making the batch size for the student larger, and so on. So you want to sort of inject as much invariance as you can, and that will make the student learn more. So they say here, noising student. When the student is deliberately noised, it is trained to be consistent to the teacher that is not noised when it generates the pseudo-labels. In our experiments, we use two types of noise, input noise and model noise. All right. First, data augmentation is an important noising method in noisy student training because it forces the student to ensure prediction consistency across augmented versions of an image. Specifically in our method, the teacher produces high-quality pseudo-labels by reading in clean images, while the student is required to reproduce those labels with augmented images as an input. Second, when dropout and stochastic depth function are used as noise, the teacher behaves like an ensemble at inference time when it generates pseudo-labels, whereas the student behaves like a single model. In other words, the student is forced to mimic a more powerful ensemble model. We present an ablation study. So this it's a bit weird what they say here. Don't be confused. You use the dropout and the stochastic depth on the student model. And they say here, if you do this, the teacher behaves like an ensemble at inference time, whereas the student behaves like a single model. And yeah, it's a bit of a weird formulation, but it's true. Like the teacher will produce these same the label for different pathways through the student if you use dropout and kind of stochastic depth, and therefore the student is kind of required to approximate each time. Each forward pass has a different forward pass through the layers, through the connections with dropout, and it's forced to approximate that teacher label with all of these different things. So you see that you put in a lot of techniques. So they have even other techniques. There is one additional trick, and it's not one. Actually, they have so many tricks, and if you look at their experimental setup, that it's crazy. Like they describe exactly, we reduce the learning rate like this, and the batch size like this, and so on. So to get state of the art on ImageNet, it's not enough to just have a good idea of a new thing to do. What you have to have the good idea and then execute it almost like really well, because you have to regard all of these additional tricks that people have figured out over the years. In any case, they say it works better with an additional trick, data filtering and balancing. Specifically, we filter images that the teacher model has low confidence on, since they are usually out-of-domain images. So that goes to a point where if you see, we have this ImageNet labeled data set, right? And we have the larger data set. Now, the larger data set simply contains images, and there is no guarantee that the images are actually of the classes that we have in the ImageNet data set right here. We have 1,000 classes here. There's no guarantee that these images fit into any of those classes. Yet we still ask the teacher model to put them in some of these classes. Now, you can filter out part of those images if you can look at the teacher model and you look at its confidence. So when it outputs a distribution, if there's just two labels, let's say, if it outputs a distribution like this, that's wildly different than if it outputs a distribution like this. Both are class 1 labels, but one is much more confident than the other. So what you want to do is you want to filter out these low confidence labels because, you know, the model isn't really sure, but it has to assign a class. But that's usually an indication that it is an out-of-domain image. So if they filter this, it works better. And then also, to ensure that the distribution of the unlabeled images match that of the training set, we also need to balance the number of unlabeled images for each class, as all classes in ImageNet have a similar number of labeled images. For this purpose, we duplicate images in classes where there are not enough images. For classes where we have too many images, we take the images with the highest confidence. Okay, so this is just another technique. This has basically nothing to do with their core idea, but this is just another thing where they say, okay, we can treat this big thing that we scrape from the internet, we can somehow filter and balance it smartly, and that will work even better. All right, so let's go into the experiments. Of course, they're so what they do, I think, where is the graphic? What they do is they take an they take an efficient net right here, and they first train an efficient net, a smaller efficient net, as we said, to be the teacher, and then they train a larger efficient net for the student. The best model in our experiments is a result of 3 iterations of putting back the student as a new teacher. We first train an efficient net B7 on ImageNet as the teacher model. So you can see in the table right here what the B7 achieves. The efficient net B7 here, you can see it has 66 million parameters, which is fairly small compared to these other kind of previous state-of-the-art methods on ImageNet, right? So they first train this, and that will achieve something like an 85% accuracy. Now, if you just train a larger model, this efficient net L2 right here, that has, you can see 480 million parameters, so a lot of more million parameters, but you just train it on the same data set on ImageNet, you will get a 0.5% improvement. And you can see that here, with noisy student training with the exact same model, so it has the same amount of parameters, you'll actually get an 88.4, so like a more than a 3% improvement. And that's with the same model, just with this different training procedure and inputting these 300 million unlabeled images that you have laying around. But all the information about, all the label information comes from the ImageNet dataset and comes from this EfficientNet B7 teacher model. So that's basically, it's a testament that out of this 85, you can make this 88 just by smartly using the information that this model has learned about the data and transferring it to new data. So they train an EfficientNet B7, that's the small model, as a teacher model. Then by using the B7 model as the teacher, we trained an EfficientNet L2 model with the unlabeled batch size set to 14 times the labeled batch size. And they stress that it's important that you up the batch size. That's another thing that makes the student learn more than the teacher. Then we trained a new EfficientNet. So, by the way, this 14 times, it can be done because now you have more data, right? So you can also up the batch size. Then we trained a new EfficientNet L2 model with the EfficientNet L2 model as the teacher. Lastly, we iterated again and used an unlabeled batch size of 28 times the labeled batch size, the detailed result of the 3 iterations, and so on. Okay, so you can see that it's a fairly complicated procedure, but you can gain and gain and gain by simply upping the or iterating on this procedure. And I think they have it somewhere here. Yes. So as you can see, if iteration 1, you train the EfficientNet L2, you started with the B7, and you train the EfficientNet A2 with a batch size 14 times larger, and you gain significantly, right? This gains about 2% over the original EfficientNet. Then you iterate again with the same batch size, and you get like a 5.5% improvement, and you iterate again with an even larger batch size, and you get a 0.3% improvement. So there's diminishing returns, but still you can see that, the more, with the introduction of noise, with the introduction of the larger model, with the introduction of the larger batch size, these are all things that help the student basically become better than the teacher. All right, so they do a bunch of other experiments. So their main comparison is right here, where they say, look, even if we train the same model with this noisy student training, we can make, pretty large gains over the same model where we do not train it with this noisy student training. So this really seems to help, due to the noise, due to the additional data. They do a lot of ablation studies, so that's pretty interesting. And they also do these studies on this special ImageNet dataset. For example, ImageNet C, you can see that there are quite a bit of distortions right here. I don't even see if you can see it on this video, but this is a swing. So the swing right here is like something like this. But you almost can't see it. And you see that the bold on the left is always the prediction of their model, while the thing on the right is the prediction of the original model. So this model, they claim, is significantly more robust to these kinds of perturbations, and they do an analysis of this where they show, yes, in fact, it is. So I think we've already seen this at the beginning, that the noisy student is significantly more robust to these perturbations, and they also test this to adversarial perturbations. So right here you can see that the original model drops pretty quickly as you increase the epsilon. The epsilon is kind of the strength of the adversarial perturbation, and the original model drops very quickly to fairly low accuracy, while as the noisy student training drops much less quickly. Now, this is another testament to the fact that what you do, I think what's happening is you have your data space, right? And you have your data points in it. Now, when you do the normal data augmentation, what you'll do is you not only force the model to predict those points correctly, but you'll sort of make a bit of a cloud around them, and you force the model to predict that cloud correctly. Now, if you introduce more data and you do even more noise, what you do is you'll make these clouds kind of larger, and that means the model is more robust to any sort of perturbations in these clouds, right? And that means it's probably also going to be more robust to adversarial perturbations. So that's sort of how you can think of this, this introduction of noise to make it more generalizable. So how does this generalize better? So if you think of this data point right here, if I'm looking to generalize, that means, I have this IID data set. So probably my test data is going to be related to the training data. So I might get a data point that's fairly close to that data point, and generalizing means I classify it correctly. Now, if this cloud is very small, like it is here, my decision boundary could be like here, right? And even though the test data set is fairly close to the original training data point, it will be classified incorrectly. However, if my original cloud during training is larger, you can see if I train a model, it can maybe put the decision boundary here, and then my test data point will be included on that same side. So that's kind of the idea behind generalizing better. Of course, that's a vast simplification. And also to say that this here is an FGSM attack. So this is kind of the weakest attack in the adversarial perturbation spectrum. They do say under a stronger attack, PGD, which is a fairly strong attack with 10 iterations at epsilon equals 16. Noisy student training improves efficient net L2's accuracy from 1.1% to 4.4%. Now this, 1.1% really means the model is almost like dead. This is lower. This is like random performance, and 4.4% is still a bit above random performance, but yeah, you could probably get there by simply using any sort of noise in that case. But still, you can see that it is more robust to especially to natural distortions, and therefore it generalizes better. As I said, they do quite a bit of ablation studies to figure out where exactly the performance comes from. And the answer is it pretty much comes from all the things that they've described. So here you can see the effect of that extra data set, and you can see pretty much with that extra data set all the situations improve. Here you can see what is happening when you do not augment the student. When you do not data augment, you can immediately see that the accuracy drops. And then when you do not augment and also don't use these model noises, then the performance drops again. And lastly, when you use the teacher but you noise the teacher, you can see also here the performance is dropping from the original quite a bit. So all of these things kind of contribute, and they do much more ablations, and they have listed their findings here. So using a large teacher model with better performance leads to better result. So, as the original teacher, you should use as good as possible a teacher model you can find. Second, a large amount of unlabeled data is necessary for better performance. Okay, so if you want to do this, you better get a large amount of extra data, because that's one thing that makes the student perform better. Soft pseudo-labels work better than hard pseudo-labels for out-of-domain data in certain cases. Fourth, a large student model is important to enable the student to learn a more powerful model. Okay, so because usually this knowledge distillation is what this is usually called knowledge distillation if you use a teacher model to train a student model, and it is often used when the student model is smaller than the teacher, because you want to kind of become more efficient. So the teacher is large, you make the student small, and you usually sacrifice some accuracy. And here they say if you want to gain some accuracy, you need a large student model. It can't be like a small one. Number 5, data balancing is useful for small models. Number 6, joint training on labeled data and unlabeled data outperforms the pipeline that first pre-trains with unlabeled data and then fine-tunes unlabeled data. So this is in contrast to like what people have done before in the self-supervised learning and so on, where it's always kind of pre-training then fine-tuning, or in the transfer learning setting. 7, using a large ratio between unlabeled batch size and labeled batch size enables models to train longer on unlabeled data to achieve a higher accuracy. Okay, we've already seen that they have used that. And number 8, training the student from scratch is sometimes better than initializing the student with the teacher, and the student initialized with the teacher still requires a large number of training epochs to perform well. This is fairly interesting because it kind of alludes to the fact that the minima in weight space, if this is of course the case if the student model is the same as the teacher model, so in like iteration 2 or 3 or whatnot, it means that in weight space, if we look at, you might want to start the student here and the minimum is right here, and you might want to think that if I learn the same thing, then the minima are fairly close together, right? So the teacher's minima might be here and the student minima might be fairly close. So it might be beneficial if I start not over here, but actually start at the teacher's minimum. But this doesn't always seem to be the case. And that is a fairly interesting observation, because it kind of means that we're talking about different minima here. We're talking about the student model learning different things. And that's what we've discussed already. The student model kind of learns to be robust. And that's probably a minimum that's fairly far away in weight space, at least in a sort of energy landscape weight space. Might be the case that it needs to actually overcome kind of a hill here, even though the minimum might be close. There's lots of research in like how minima are distributed in these weight spaces, which I don't want to go into right here, but it is a fairly interesting observation that it's not always helpful to initialize the teacher student at the teacher's optimum. Okay, so this was the paper, and this is the type of research where I do appreciate kind of these large labs taking it on, because they have the resources to do all of these ablations, all of these different models, cross them with these giant data sets and so on, which I guess university labs just would not have. And this is a fairly thorough paper, really investigating which parts of the pipeline do something and which ones don't. And usually I'm fairly critical of pipelines that have like 50 billion tricks, because you never know where the improvement exactly is coming from. But you can sort of mitigate that criticism by doing all of these kind of ablations on the different parts and really showing, look, this is important, but this is also important, but this is also important, but this is also important. So yeah, that was my 2 cents to this paper. I hope you enjoyed this, and I'll see you next time. Bye-bye.